So hello everyone. I'm here to talk about our project, which is full stack image super resolution using deep learning. So I'll just get into it. To briefly introduce the concept of image super resolution or ISR, ISR is all about enhancing the quality of low resolution images by reconstructing the finer details to produce some high resolution outputs. So this method or this technique has tremendous applications across various fields. So you can think about improving the clarity of medical images, or which could perhaps give better diagnoses. Then there is enhancing satellite imagery for, say, environmental studies. You could also deliver some really high quality videos for streaming services. So the applications are endless. Traditionally, the way ISR used to be performed is it used basic interpolation methods like bilinear or bicubic approaches. So while they are computationally efficient, but these methods did not give results as good as some of the methods that have come up. The older methods often resulted in blurry or low quality outputs, especially when they needed significant upscaling. With deep learning on the rise, we now have powerful tools like CNNs that can model these complex relationships between the low and high resolution images. And in our project, we have focused on three well known models, which are SRCNN, VDSR, and EDSR. More about them later. So we have trained these models on benchmark dataset called the div2k dataset, and we've also built a web application using Streamlit to make our solution interactive and practical. So on this platform, users can upload an image and see the results on the models generated shortly after. Uh, about the literature review that we did, one of the first milestones in the field of super resolution, image super resolution, was the introduction of SRCNN in 2014. So this pioneered the use of neural networks for ISR. It was a very important foundation. It laid a very important foundation. It's a relatively simple three-layer model, but it sets the stage for deep learning-based solutions over traditional interpolation-based ones. Building on that, there is VDSR, which was proposed in 2016. It took things further by using much deeper network along with residual learning. So this approach addressed challenges like vanishing gradients and made training deep models more practical. Around the same time, we have FSRCNN, which focused on efficiency by performing feature extraction in low resolution space. And this enabled large real time applications for resource constrained devices as well. Then there was ESPCN, which introduced subpixel convolution, a novel approach that's especially effective for video super resolution. Then there's approaches like SRCAN, which brought in generative adversarial networks. This model made significant strides by focusing on perceptual quality and generating photorealistic textures. More recently, researchers have explored attention mechanisms like RCAN to adaptively focus on important features and multi-branch architectures to improve further performance. So the later methods that I mentioned are more computationally intensive. So for the course of this project, we focus on the lighter earlier ones, which are also the foundational methods. Onto the dataset that we use the div2k dataset, which is a gold standard dataset for image super resolution research. It contains 1,000 high quality RGB images that are both diverse and quite challenging. They are from a lot of varied environments, and this kind of makes it an ideal dataset for training and evaluating our ISR models. So the dataset is split into 800 images for training, 100 for validation, and 100 for testing. To simulate real world scenarios, the dataset provides low resolution images of each image at various downscaling factors. Like we have downscaled images to 2x, 3x, and 4x. This allows us to evaluate model performance while working on different scales of degradation. For pre-processing, we focused on the YCBCR color space, where the Y channel represents luminance. So this channel is crucial because for super resolution tasks, we need the channel that contains the most information, and this is the channel that helps us with that. For higher resolution images, we resize to a uniform patch size of 96 by 96 pixels. Low resolution images were downscaled by the required factors, and in some cases, they were upscaled using bicubic interpolation. So this was done to match the dimensions needed by some specific models like the srcnn. Finally, the process images are converted into pytorch tensors, which helps with the training with acceleration on gpus. um, so onto the models that we use, we began with the SRCNN, which is one of the first neural network based approaches for ISR. It consists of just three convolutional layers. The first layer extracts features from the low resolution input. The second layer maps these features non-linearly to capture complex relationships. And the final layer reconstructs the high resolution output. Despite its simplicity, SRCNN laid the groundwork for more advanced models to come. Next, we have the VDSR, which builds on SRCNN by significantly increasing the network depths to up to 20 layers. For this project, we have chosen 18 layers. Deeper networks usually face challenges like managing gradients, but VDSR performs residual learning to avoid that. So instead of predicting the entire HR image, it learns to predict the residual, which is the difference between the input and the target image. So this makes training much faster and improves accuracy, particularly for large upscaling factors. Finally, we implement the EDSR, which is an optimized version of residual networks. It removes batch normalization layers, which can sometimes hinder performance in ISR tasks. EDSR also scales its residuals, improving stability during training. For training, we use the div2k dataset with the mean squared error as our loss function. Then we have the Adam optimizer. Which was chosen for its ability to adapt learning rates efficiently. And we started with the base rate of e raised to 10 to the power minus 4. To prevent overfitting, we employed early stopping by monitoring the validation of PSNR. Uh, yeah. And to evaluate the performance of our models, we relied on the following metrics, which are the PSNR and SSIM. So peak signal to noise ratio. It measures the fidelity of the reconstructed high resolution images compared to the ground truth. It calculates the ratio between the maximum possible signal power and the noise introduced by the reconstruction process. So higher PSNR indicates better quality of reconstruction. So second metric is the structural similarity index, SSIM, which instead of just comparing pixel values, SSIM evaluates how well the reconstructed images preserve the qualities of the original. Uh, so 1 is the perfect score here. It ranges from -1 to 1. We choose these metrics because together they provide a balanced assessment of image quality, combining both pixel level accuracy and image similarity. So these are the results that we obtained. Yeah, starting with the PSNR values, SRCNN achieves 27.89 decibel value. This is a good baseline, but then we moved on to the more advanced models. So VDSR gives a better PSNR value over here. And finally, EDSR gives the best value over here uh, with the value of 32.41 decibels. In terms of SSIM, we see a similar trend. We see increasing values of SSIM going from SRCNN to VDSR to EDSR. And although EDSR outperforms the other models, but the difference is not large. Is not large. It's not drastic. So this shows that there is a strong foundation laid by SRCNN and VDSR, and it highlights how all of the models can be like viable for super resolution tasks. We also developed a web-based application for hosting our models where users can see the results being generated for their input low resolution image in real time. Now onto the demo. Here we have a platform which allows us to upload images in any of the popular formats. So here we have the original image displayed, the low resolution image. And here we have all the three of the models trying to generate the output. And after the generation is complete, we also have the performance metrics, which include the time taken to generate these results, and also an assessment of the quality, which is in the form of PSNR and SSIM values. We also have functionality to download the resultant images by clicking on these buttons. And that's about it for the demo. Thank you.